Hello, my name is Dr. Gleisner, and we're talking about the deceptively simple matter of matter. And in the specification, there are three states of matter: solid, liquid, and gas, as you can see down there. And the simple idea is that you have essentially a box full of spheres, or in fact circles, which are orderly arranged in an orderly fashion. Then you've got spheres, you've got spheres arranged in an orderly fashion which are all touching, therefore that's a solid. Then you've got spheres arranged in a chaotic fashion, more or less, but they're mostly still touching with tiny little gaps between them. And then you've got a box with very few particles. Now, the idea is that the forces between the particles, as indicated by the spheres, tell you whether something is in fact a solid, a liquid, or a gas at room temperature and standard pressure. Here's the thing though. If you heat something up, then if it was a solid, there's a good chance it will melt. So it will change from a solid to a liquid by melting. And then it will change from a liquid to a gas by boiling. And of course, the reverse is true. If you cool down a gas enough, you can make it into a liquid, and that's condensation. And then from a liquid going to a solid is called freezing. But there are three limitations to this model, and those are that in this model there are no forces. That means now, explicitly, there aren't any forces between the particles. So how come they hold together in a solid, or how come they are actually holding together in a liquid? And what we've got here is the sort of distinction between explicit forces and implicit forces. So implicitly, there are forces between those particles, and those are intermolecular forces. And I already talked a little bit about them, van der Waals forces, for example, but also we've come across them in electrostatic attraction, in ionic solids, and so forth. And so what we're simply sort of hand-wavingly are explaining as there are no forces is that we are not explicitly stating those forces, but there are forces between the molecules which clearly hold them together, and the temperature at which the solid or the liquid or the gas is determines whether the particles have sufficient energy to overcome the attraction between them. So that's the first complication. Then the second one, the second limitation of this model, is that we have spheres. And to all intents and purposes, that's all right. As a model, that's fine. So if we're looking at oxygen and nitrogen, we know that they are basically two atoms bonded together. They are twins, as we say. And then carbon dioxide can be represented as a molecule with three atoms stuck together. But from the outside, more or less, it doesn't really matter that they have not an entirely spherical shape. They can be represented as spheres for our purposes for the most part. This then gets a little bit more complicated with more complicated materials. But we'll come to that later. This whole model of particles in the state of matter is already very powerful, because it tells you whether how particles behave based solely on their appearance at, let's say, room temperature and standard pressure. And I will talk about that more in a little bit more detail in a later video. Okay, so these are, however, the minimum keywords that you need to remember melting, boiling, freezing, condensation. And of course, if you have dabbled in science before, then you might know that there are other states of matter, but they don't exist in standard conditions. So what we normally say here is that over a fairly standard range of temperatures, not exotic ranges, not like millions of degrees and not like near absolute zero, most gases certainly behave like ideal gases. That means they have no forces between them, and they can be represented as these spheres. So we can treat them as solid inelastic spheres with no forces between them.
Please like and subscribe and let me know of any questions you'd like me to cover in the comments.